is all about the shell method. If you've not watched the video in discs and washers, make sure you do that first. But if you have, come join us and let's learn how to use the shell method. Today we're going to learn all about the shell method. If you've not done the disc and washer videos, make sure you go and you do that now. And if you have, let's get going. So with the shell method, this first example you have, you want to make sure that you graph it on a piece of paper. You have to sketch it out. And we know in this problem, we want to revolve this problem around the y-axis. The first step you have to do is draw a graph of the function and what they want the problem to be. So we have this function graphed. We're going to revolve this function around the y-axis, and our bounds are from 0 to 2. So the second step is draw the reflection so you can see the volume that this is going to create. Remember, we want this to revolve around the y-axis, so we drew the reflection on the other side. From previous lessons, you can learn that you can either use a disc or a washer. Well, in this case, it would be a washer because there's a hole in the center. Okay, when you use a washer, you have to draw two circles. So our inside ring will be right here, the middle piece. And then our big circle ring will be from side to side. So the next step would be to find the radius. If we go to draw on the radius of the small circle, it hits our blue function. But then the radius of our big circle, notice it hits the same function. So when you have this issue, you can no longer use a washer. And you have to use the new method called the shell method. So that's how you know when to use the shell method. If the washer isn't going to work, you can go ahead and use the shell method. Let me show you how that works. So you still have the shadow, but now let's draw in what a shell is going to look like. The shell will have a circle still in the center, but this time it'll have legs coming straight down. So what the shell method is doing is creating a bunch of cylinders. That's what we're going to be doing. Or people call it cans. It looks like you're stacking cans on top of each other. Now let me show you what this is going to look like in a 3D form so you can see the volume that we're creating. As we look at our 3D version, you can see I have our function plugged in here and our bounds plugged in. So the first thing here is our function. You need to picture the shadow on the other side. The shadow is going to be over here. Now watch as I start dragging these shells throughout the function. And you'll notice they look like a can or a cylinder. And we're going to be adding up all of these cylinders all across the function, all the way to the other side. Notice how thin it gets at the other side. All right. But now let me show you what it looks like as we build it all the way across. So as we build those cylinders or those cans all the way across our function, you'll see this brown shape coming in, and at the very end you'll see that full shape, and this is called a shell. So building all of those cylinders all the way through the function, you end up with this volume shape, and it's called a shell. This is the volume that we are going to be finding in our problem. So now that you've seen those 3D shapes, you see that we're creating a bunch of cylinders or cans here, and when we stack all those cans together, this is the volume shape you're getting, and that is called the shell method. So how do we figure out how to solve this kind of problem? Again, we're talking volumes. We need 3 dimensions. For example, with a disc and a washer, you use circles to find the area, and then our third dimension was either the dx or the dy. Similar process here. We're going to find the area of the shell or the cylinder, and then our dx or dy will be our third dimension to produce the volume. So let's think about a cylinder for a second. If you see right here, this is like an example of a cylinder, all right? But how do we find the volume of this? Well, let's say I cut down one side of the cylinder and I lay it flat. What shape do we have? We have a rectangle. So what we're going to do with these shells is find the area of this rectangle, multiply it by dy or dx, and that will be the volume of our shells. So let's write this out. So for a shell, you're going to draw a rectangle to show how we're going to find the area of the cylinder. And what we need to figure out is area of a rectangle, right? Our base times our height. So what is the base of our cylinder? Well, if you put your cylinder back together like this, right? Our base is this top piece. When you open it up, it's your rectangle, but when you put it back together, what shape did you make? You made a circle. So we need the circumference of our circle to be our base. So anytime you do the base, you're going to do 2 pi r because your base is your circumference of your circle. And then for the height, what are we going to do for the height? Well, if you look over here at the height of these legs hits the function that we're using. So the height is going to be whatever your function was that was given for the problem. And then your width, notice your width, we're stacking these legs along the x-axis. So this is the width, so this is going to be a dx problem. Because the legs of the shell hit the x-axis, it's going to be a dx problem. That's really important to know. It's wherever the legs of the shell hits decides if it's going to be a dx or a dy problem. Okay, well now let's set up this problem. So we know our base, I'm going to rewrite it down here, is 2 pi r. So what's the radius of this function? So right here, you're going to go out. And it's going out some x value. We don't know what that x value is, but it's going out because it's moving horizontally. It's going out some x value. So your radius is just going to be x. So let's go ahead and set up our problem. Our integral is going to be from 0 to 2 because those were the bounds we were given. The area of our rectangle was 2 pi x, this is our base, times our height, which is our function. And our function was negative x squared plus 2x dx. So this right here is your base. This piece right here was your height, and this piece was the change in x, which gives us our 3 dimensions for our volume. From here, you're just going to go into your y equals in your calculator, stick in this equation, evaluate from 0 to 2, and you should get 8.377 for your answer. And that's how you do the volume of a shell. For this next function, we're doing 2 times the square root of x. They want it bound between 2 and 9, and our axis of rotation is x equals negative 2. So the first step is to draw a picture of what it is that they're looking for. And then your second step is to draw in that shadow. So let's do that now. So we're rotating around x equals negative 2. So we have to account for this space here first. So I'm going to move it right here. And then my function will go up this way. And then we have 2 here. So I got to cross this one here. And I got to cross one over here. Here is the original space that we want to revolve around the line x equals negative 2. This is the shadow that it is going to create when we revolve that line, when we revolve that function around x equals negative 2. Now let's go ahead and draw in what a shell would look like for this when we revolve it around x equals negative 2. So there would be the top of our shell, and now we need to draw in the legs of our shell. The reason, again, that we're using the shell method for this problem is because if you tried to use a washer, the inside circle and the outside circle would both hit the same function. Therefore, we have to use the shell method. And for the shell method, what are we using? We're using cylinders. And what happens when you cut the side of a cylinder and open it up? You have a rectangle. So the next thing I'm going to write down is my rectangle and write out the equation for our function. Remember, for a shell, the shells are really cylinders that are being stacked. And if you cut the side of a cylinder and open it up and lay it flat, you have a rectangle. So let's write down a rectangle and write down our dimensions to find the answer for this shell problem. Here's a picture of the rectangle where we need to find the area. The base of this shell is this circle part up here, remember? So that is your circumference. So it's going to be 2 pi times your radius. What is the radius of this? Well, now look. We're coming around x equals -2, and it's going all the way out to some x value. So again, when you're finding distance, you have to do right minus left. So for this radius, it would actually be x minus a -2. Because we're going out some x distance, but that's just from 0. We have to acknowledge that it's rotating around x equals -2. So that way your radius will actually be x plus 2 when we go to write it out. Now what's your height? Of course, the height is the function that it hits. And then the legs are along the x-axis, so this will be a dx problem. So let's set up our integral from 2 to 9, because those were the bounds we were given. 2 pi x plus 2 times our function, which was 2 square root of x dx. So this was our circumference. This is the height, and our dx gives us our third dimension for volume. Go ahead and stick this into your calculator, into your y1, and put the bounds from 2 to 9 for your integral. And the answer you should get will be 508.664. For this shell problem, I want to show you what happens when it's a dy problem instead of a dx. So again, the first thing you're going to do is you're going to graph what they give you, and then you have to go ahead and graph in the shadow. So let's go ahead and graph in the shadow piece now. So hopefully now you have the shadow part graphed. And if it helps you, get a highlighter and highlight the original piece and then the shadow piece that is being reflected in this problem. Also, sometimes it's helpful to show, okay, this function is rotating over the x-axis, so you remember which way to rotate it correctly. Now let's set up what a shell looks like when it's being rotated over the x-axis. So your open circle is going to be here, and then the legs of your shell are going this way. So again, we still have a cylinder, so we're still going to use a rectangle to set up our problem, but this time the base is actually the legs. Right? This is the base of your shell. So your base of your shell is hitting the function. So this time our base is just going to be whatever our function is. And the circumference part of our shell ends up being right here. So this will be our 2 pi r. And notice the legs of our shell hit your y-axis, so these will be tiny changes in dy, because now our cylinders are being stacked against the y-axis. That tells you who the boss is. That tells you which variable you need when you're writing out your function. So let's go ahead and set up our integral now. Our integral is going to be in terms of y, since this is a dy problem, which is convenient because they gave us 2 to 3. Our 2 pi radius, so 2 pi, our radius for this function, notice, is this way. So the radius will be some y value this time, since the radius is going up and down. So 2 pi y for our radius. Now for our base, we plug in our function. Well, look how nice they already did this. They already have our function written in terms of y for us. So 2y and then dy. Now to get the answer, you're going to put this into your y1 in your calculator, but just put the y values in as x. So let me show you. So in your calculator in y1, go ahead and put in 2 pi x, 2x, and then evaluate from 2 to 3. But what's important here is this has to be what you write down for what you're solving, since this is a dy problem. When you plug this into your calculator, you'll get 79.586 7 for your answer. Hopefully this video helped you learn how to use the shell method effectively, but I always suggest trying discs and washers first because honestly, I think they're easier to do. Make sure that you subscribe and share this video with another calculus friend.